process that initiates lightning discharges remains a topic of intense scientific investigation. While the exact mechanisms are not yet fully understood, several theories have been proposed to explain how lightning begins. One prominent theory involves cosmic rays, high-energy particles from outer space that constantly bombard Earth's atmosphere. When a cosmic ray collides with air molecules, it can create a cascade of secondary particles, including electrons. These electrons can then initiate a runaway breakdown process within a thundercloud. This breakdown happens when the electric field inside a cloud becomes strong enough to accelerate free electrons to high speeds. As these electrons collide with other air molecules, they ionize them, creating more free electrons and positive ions. This process quickly escalates, forming a conductive channel known as a leader. Leaders propagate through the cloud, eventually connecting to the ground or another cloud with an opposite charge. Once a conductive path is established, a return stroke occurs, which is the bright flash of lightning that we observe. The return stroke is a massive discharge of electrical current that travels back up the channel created by the leader, neutralizing the charge difference. Traditional theories, such as the cloud-to-cloud theory, propose that lightning occurs due to the potential difference between two clouds with opposite charges. While this theory explains some lightning events, it does not fully account for all observed lightning characteristics. For example, it does not explain how the initial breakdown process occurs within a cloud to create the necessary conditions for lightning. In addition to cosmic rays, other factors may also contribute to lightning initiation. These include atmospheric conditions such as temperature, humidity, and wind patterns, as well as the presence of aerosols and other particles in the air. Florida Lightning Research Center is at the forefront of lightning research. One of their key methods involves launching rockets with wires into thunderstorms. This technique allows researchers to artificially trigger lightning strikes, enabling them to study the phenomenon up close. The rockets are equipped with thin copper wires that are grounded to the earth. As the rocket ascends into the cloud, the wire creates a conductive path between the cloud and the ground. When the electric field in the cloud reaches a certain threshold, a lightning strike is initiated, following the path of the wire. This controlled environment allows researchers to make precise measurements of the electrical currents, voltages, and magnetic fields associated with lightning. They also use high-speed cameras to capture the lightning discharge process in detail. The data collected from these experiments is used to improve our understanding of lightning physics and to develop better lightning protection systems. Lightning poses a significant threat to human life and infrastructure. In the United States alone, lightning causes an average of 50 deaths and hundreds of injuries each year. It also causes billions of dollars in damage to buildings, power lines, and other infrastructure. Effective lightning protection systems are designed to safely divert lightning currents to the ground, preventing damage and injury. These systems typically consist of air terminals, conductors, and grounding electrodes. Air terminals, also known as lightning rods, are installed on the highest points of a building to intercept lightning strikes. Conductors are used to connect the air terminals to the grounding electrodes, providing a low impedance path for the lightning current to flow to the ground. Grounding electrodes are buried in the earth to dissipate the lightning current safely. The design and installation of lightning protection systems must comply with national and local codes and standards, such as those developed by the National Fire Protection Association and Underwriters Laboratories. These codes specify the requirements for the materials, dimensions, and installation methods used in lightning protection systems. In addition to lightning protection systems, surge protective devices can also be used to protect electronic equipment from lightning surges. Surge protective devices are designed to limit the voltage that can reach sensitive electronic components, preventing damage from lightning-induced voltage spikes. These devices are typically installed at the service entrance of a building or at individual electrical outlets. The effectiveness of a lightning protection system depends on several factors, including the design of the system, the quality of the materials used, and the installation methods. It is important to have a qualified lightning protection contractor design and install the system to ensure that it meets all applicable codes and standards. Regular inspection and maintenance of lightning protection systems are also essential to ensure that they remain effective over time. The inspection should include a visual examination of all components, as well as electrical testing to verify the integrity of the grounding system. Any damaged or corroded component should be replaced promptly. The study of lightning is a complex and ongoing process. While significant progress has been made in understanding the phenomenon, many questions remain unanswered. Further research is needed to fully understand the mechanisms that initiate lightning discharges and to develop more effective lightning protection systems. One area of ongoing research is the development of advanced lightning detection systems. These systems use a variety of sensors to detect lightning strikes in real time, providing valuable information for weather forecasting and lightning warning systems. Another area of research is the development of new materials and technologies for lightning protection. These include advanced air terminals, conductors, and grounding electrodes that can provide better protection against lightning strikes. The ultimate goal of lightning research is to reduce the risk of lightning-related injuries and damage. By improving our understanding of lightning and developing more effective lightning protection systems, we can create a safer environment for people and property. Firstly, understanding the underlying principles of electricity is crucial for comprehending lightning. Secondly, electricity is the flow of electric charge, typically in the form of electrons. Thirdly, these electrons move through a conductive material, such as metal, when subjected to an electric field. The electric field is created by a difference in electric potential, also known as voltage. Voltage is the measure of the electrical potential energy difference between 2 points. The greater the voltage, the stronger the electric field and the greater the force on the electrons. The flow of electric charge is measured in amperes, often referred to as amps. 1 amp is defined as the flow of 1 coulomb of charge per second. The relationship between voltage, current, and resistance is described by Ohm's law, which states that voltage equals current times resistance. Resistance is the opposition to the flow of electric current. It is measured in ohms. Materials with low resistance, such as copper and aluminum, are good conductors of electricity. Materials with high resistance, such as rubber and glass, are good insulators. In the context of lightning, the atmosphere acts as an insulator, preventing the flow of electric charge between the ground and the clouds. However, when the electric field in the atmosphere becomes strong enough, the air can break down and become conductive, allowing lightning to occur. The breakdown voltage of air depends on several factors, including the humidity, temperature, and pressure. Under normal conditions, the breakdown voltage of air is around 3 million volts per meter. This means that a very strong electric field is required to initiate a lightning strike. Thunderstorms are the primary source of lightning. They are formed when warm, moist air rises rapidly into the atmosphere. As the air rises, it cools and condenses, forming clouds. Within the clouds, ice crystals and water droplets collide, creating static electricity. The exact mechanisms that generate static electricity in thunderstorms are not fully understood, but it is believed that the triboelectric effect plays a significant role. The triboelectric effect is the transfer of electric charge between two materials when they are brought into contact and then separated. In the case of thunderstorms, ice crystals and water droplets collide and exchange electric charge, resulting in a separation of charge within the cloud. The positive charge typically accumulates at the top of the cloud, while the negative charge accumulates at the bottom. This separation of charge creates a strong electric field between the cloud and the ground, as well as between different parts of the cloud. When the electric field becomes strong enough, a lightning strike is initiated. There are several different types of lightning, including cloud-to-ground lightning, cloud-to-cloud lightning, and intra-cloud lightning. Cloud-to-ground lightning is the most common type of lightning and the most dangerous. It occurs when a channel of negative charge, called a step leader, propagates from the cloud towards the ground. As the step leader approaches the ground, it induces a positive charge on the surface. When the step leader gets close enough to the ground, a streamer of positive charge rises from the ground to meet it. When the step leader and the streamer connect, a complete conductive path is formed between the cloud and the ground. A return stroke then travels back up the channel, carrying a large electric current. Cloud-to-cloud lightning occurs when a discharge of electricity happens between two clouds with opposite charges. Intra-cloud lightning occurs when a discharge of electricity happens within a single cloud. Lightning can cause significant damage to buildings and other structures. When lightning strikes a building, the electric current can travel through the building's electrical system, causing fires and explosions. Lightning can also damage electronic equipment, such as computers and televisions. To protect buildings and other structures from lightning protection systems are often installed. These systems consist of air terminals, conductors, and grounding electrodes. The air terminals are designed to intercept lightning strikes, while the conductors provide a path for the electric current to flow to the ground. The grounding electrodes are designed to dissipate the electric current safely into the earth. In addition to lightning protection systems, surge protective devices can also be used to protect electronic equipment from lightning surges. These devices are designed to limit the voltage that can reach sensitive electronic components, preventing damage from lightning-induced voltage spikes. Lightning is a fascinating and powerful natural phenomenon. While it can be dangerous, it also plays an important role in the Earth's atmosphere. Lightning helps to regulate the Earth's electrical balance and can also contribute to the formation of ozone. The study of lightning is an ongoing process, and there is still much to learn about this complex and fascinating phenomenon.